Um, and today we'll have a last lecture of Sam DeHority from the Perimeter Institute, Orientifold lines and CoHA modules. Sam, please.
Great. Yeah, thank you. And thanks again for the invitation to give these lectures. So we're going to continue talking about CoHA modules, Orientifold lines. The basic plan is to explain in a little bit more detail this twisted vertex Drinfeld condition, why it's true that these modules that we constructed satisfy this condition. And then we'll relate this to a regular, so non-meromorphic uh, module category for this box tensor with singularities resolved in certain cases when we're able to construct this. And I should say that some of this really is a work in progress. So the corresponding result for the actual tensor structure rather than the module structure has been is much further along in the process of being done, but I'll sort of try to explain what we've done and what is mainly conjectural. So recall the main sort of construction from last time is the construction of this vertex coaction. So we have some algebra structure on the cohomology of a moduli stack, and then this nice module on the cohomology of its fixed point stack. And the sort of main properties that this satisfy are a version of vertex associativity, except now we have singularities instead of just along the diagonals as you get for vertex algebras. We also have singularities along anti-diagonals. But of course these are all kind of dual notions. So if we start with some vertex tensor product, vertex coproduct, then these are dual to things that are much more similar to our familiar operations. So if V is the, let's say, graded dual vector space to HM, then we have a product action with singularities and a module action also with singularities, cohomology of M sigma dual, the tensor B. But somewhat confusingly from sort of usual notions for vertex algebra modules, we get that the associativity isomorphism now has are two different expansions of the same Laurent series that bivariate Laurent type series that has singularities now not just on the diagonal when the two sort of points where our algebraic operation happens simultaneously, but also along the anti-diagonals where they live on different sheets of this this orbifold. So we could imagine this as some sort of picture. If we are living on flat space, we have this Orientifold point, and we have some sort of line that lives at that Orientifold. Then we get singularities not only when our module object at the Orientifold point interacts with our our sort of non-Orientifold line, but we also get singularities when that line interacts with its its image under the Z mod 2Z involution. So we have kind of two we have an additional type of singularity that makes this sort of non-local in a kind of unusual way. The other main identity that this module satisfies is this, I don't know, also somewhat strange type of identity, which we can express both as a string diagram pictorially, and then also in terms of a commutative diagram or a chain of operations of a compatibility between the action map and the vertex coaction map and additional data on our sort of just pure algebraic structure A. So what's the string diagram? Well, this is the definition of this twisted vertex Orientifold category, all relative to some underlying simple module category. It says that if we have our algebra, it acts on one of our lines, and we coact. We can express this in terms of some other data. So if you wanted to write it in terms of symbols or formulas, it would say something like, if we take the left vertex coaction of an element A acting on a module element M, then this has some complicated expression with terms that look like the left coaction of the elements M, and other data. So the actual formula in terms of symbols is kind of a mess to write down because of the braiding, but you can express this in terms of the following commutative diagram. It says that this diagram that we draw here actually commutes. So let's sort of trace the diagram and see what.
I just don't understand the identity, the diagram, string diagram identity when you have a three lines merged together.
Three lines. So we have vertex associativity, and when we have three, we mean so there is a slight ambiguity. So three lines merged together is a triple product, which is an associative product. But when we have three lines that sort of co-emerge together, we always mean that this is kind of coming out from the left. So this expression
using some sort of a co-multiplication.
Exactly, yeah. When they separate, you use a co-multiplication, which is co-associative as rational functions.
Okay, well, thank you.
Great. So the identity is this particular chain, and let's sort of go through what the diagram says. Well, it says, well, we act and then we coact, which is the top row of the diagram. And this is the same thing as we take this double coproduct on the algebra and coact from our module object. We apply this chain of braidings. So we swap the sort of second strand, the final strand of our algebra with our the strand that we coacted from, and we swap the second and third strands with this braiding. We do some additional braidings, so we use this reflection on the last term, which is now after the braiding close to the original strand, and then one additional braiding of the strand that has now crossed underneath with the first strand. Finally, the sort of middle object in our triple coproduct has been made adjacent to our module, so we can act with it. and then we multiply all of the first three resulting strands together while acting with the now new strand closest to the module, and that these two things are equal to each other. So where does this identity come from? Well, it comes just geometrically from our description of these modules in terms of fixed point stacks. And I'm going to give a proof sketch to sort of highlight how you might have come up with this identity yourself.
Sorry to bother you. In your commutativity diagram, so the action of A from to M, that also should be involving a parameter. And
no,
the coaction also be involving a parameter. So by the end, it should be receiving two different parameters.
Yeah, so the action actually has no parameter. So the
action does not have a parameter. Only the coaction has a parameter.
Right. We genuinely have an action, but the coaction has singularities.
I see. So the coaction is only vertex.
Exactly.
In the vertex operator sense. Okay, thank you.
So yeah, what's the idea behind the proof? Well, the idea is you look at the same structure for just the algebra itself, and then you try to see you know, how to generalize this proof to this folded case. And how do we get the bialgebra identity? So how do we get the identity which is if the vertex coproduct of a product of two elements A times B is equal to, you know, the appropriate braided version of the product of and here our multiplication involves the braiding delta Z of A and B. Well, we want to get the identity of these two string diagrams. Both of them correspond to some like geometric correspondence, so we can write each of these diagrams as some correspondence over m times m times m times m, corresponding to the you know, 4 external legs of these two diagrams. So if we have terms that we'll label as A1, A2, B1, and B2, which live A1, A2, B1, and B2 live in these moduli spaces, then let's just write down what it is that each of these two correspondences parameterize. So the left-hand side, well, it consists of first an extension of the objects A2 by A1, and then we want to do the opposite of an extension. So we want to write C up to some localization term as the direct sum of two other elements, B1 and B2. So that's what this data parameterizes up to a normal bundle that gives a localization factor in cohomology. But what does the right-hand side give? Well, it says that we're going to write A1 as a direct sum of two things. So A1 is a direct sum of A11 and A12. So we would then write A2 as a direct sum of A21 and A22. Then we express, we can take extensions of A11 by A21, and that's going to be our element B1. Extensions of A12 by A22, that's going to be our element B2. And up to localization terms, these two diagrams are supported on the exact same locus, the locus of extensions of direct sums so that the extension itself is a direct sum. So the calculation, which takes a couple of lines, writes down all of the appropriate localization factors, and then they turn out to cancel, and you get this identity. Now the idea in the folded case is just to do the exact same thing, to take the left-hand side of this corresponding diagram and calculate it using localization. It helps to have an explicit description of what this the fiber of our folded short exact sequence diagram looks like. And you can just write down explicitly what this is. So if we have A, which lives in M, Xi, which lives in M sigma, Eta also lives in M sigma, we're looking for the fixed points of the length 2 filtration objects under the assumption that our middle object is fixed. And so what does this consist of is, well, our length 2 filtration consists of an object A, which is forced to be isotropic, so it's sitting inside of its orthogonal complement, which is sitting inside of our fixed object Xi. Then this is our set of inclusions that forms this sort of convolution of 2 short exact sequences. So here we have psi modulo A, and then here we have psi modulo A perp, which is equal to sigma of A. And we can conveniently encode all of the data of this diagram in the following diagram where, sorry, this is actually eta. And then C is equal to the quotient of A perp modulo A, which is forced to have an invariant pair. So this lives in M sigma. So we're kind of taking our object C, and we're extending it by an object A in a way that in the resulting extension, A is forced to be isotropic in that extension that we call eta. So all of this is encoded in this sort of composition of 2 short exact sequence diagrams. And then if you do this, what is the left-hand side of the identity that we want? What's the left-hand side of this diagram? Well, our left-hand side is, well, we just have exactly this type of extension. So we have an isotropic elements A in Xi, and then we can write Xi as the like classical type version of a direct sum, which is a direct sum of one object together with some isotropic object and its dual under the involution. And we want to compare this to the right-hand side. On the right-hand side of this diagram now has a ton of objects. So if we have our object A is here, eta is here, C is here, C is there, Then for each kind of internal leg on this diagram, we're going to assign some sort of name, keeping track of the data. So A1, A2, A3. We want to keep track of this intermediate object, like mu, which is after we apply the corresponding extension. And then we also have B, which is the strand. We just assign names to all of the strands of this diagram, and then see what happens if we impose the relations imposed by the correspondences from each leg. It turns out this diagram is a large diagram that looks like this. So our isotropic sub-object up to localization factors splits as a direct sum of three terms, A1, A2, and A3. And our both of our object, which is going to be the thing we're extending by, and our object at the end, split as these kind of modified versions of direct sums. And then we just want the corresponding pieces to lie in the corresponding direct sum factors. So we want C to be an extension, a double extension of A1. So we extend this element B, which is the sum end factor of C by A1, call that element epsilon, and we further have an extension of the dual of A3 by that epsilon. And then all of the duals of this corresponding data, and then you write down both of these diagrams, all of the localization factors that you need in order to identify the cohomology classes of these diagrams with the algebraic operations that were written. Those localization factors all cancel out, and you like show the corresponding identity. And it takes I don't know, a couple of pages of work to keep track of all of the localization factors and do the calculation. But hopefully this argument explains why it's not unthinkable that you would get a relation of this type, and that this actually is the corresponding diagram.
Do you need it to be an involution, for example, if it's a root of unity?
So yeah, sigma is well, it's an anti-involution, so it flips extensions of the corresponding diagram. We had assumed from the beginning that sigma was an anti-involution of the abelian category. So in particular, it exchanges the orders of factors of extensions.
Yeah, but you can look for fixed points of the cyclic group action. It maybe do not like kind of to be messed with commutativity morphism, but still, because you know, kind of it's pretty dry. You define something. Okay, I know what CoHA is, and I don't know why one should kind of try to do the Orientifold. Maybe physicists are happy, but why mathematicians should be happy with this particular modules on the CoHA? Why do you need involution at all? I mean, there is just, for example, a question about the category of lines themselves without any extra structure. All right.
Right. So what we're interested in is constructing you know, if we're interested in the category of lines, this is a categorification. So whatever our lines are, this is some categorification of the K theory of that category. together with its tensor product. And this is some associative non-commutative algebra. And you might be interested in its representation theory. If you're interested in, I don't know, representation theory of algebra. And we know that this category of lines, it acts as a module category on the category of like lines at an Orientifold point. And then this, by taking its growth indeed group, gives us the K theory of our Orientifold lines. And this gives us a module action for this associative algebra on that corresponding K theory. So the project of writing it this way is if you're already interested in some categorification of the algebra of K theory classes of lines, then this construction tells us something about some interesting class of representations that algebra. That's not where this project started. This project started with like trying to construct like current realizations of twisted Yangians and other sort of co-ideal subalgebras, which people have been studying for a long time, and only recently have people made progress in understanding their sort of current realizations. These sort of twisted Yangians are hard to study. They don't have a lot of the nice kind of features of the Yangians themselves with all of their different presentations and ways of relating them. And so the way the project came about is to try to understand precisely how to use cohas to construct co-ideal subalgebras of the quantum groups that we care about. So that was sort of how we started this project. This is the structure that ends up coming out of trying to answer this question.
No, but I do not, you see, I do not understand, because it's pretty formal construction, all right? You even do not care much about the details of the definition of CoHA. You assume that it exists, and then whatever, it's pretty formal. So, for example, if I am interested, like indeed representation theory, representations of twisted Yangians, so how do I construct them from what you told us?
Right. So, I guess that was what I was going to then talk about, is how from this category, you might hope to get co-ideal subalgebras of Yangians under the assumption that the Yangian itself is its modules are the category of lines are in our original theory. And we're going to do this via a version of the Drinfeld center in this meromorphic case. So we want to take this category that we have. It's sort of complicated.
Which category? Because the notation is so complicated that I cannot even remember them all. So what's the category?
Yeah, so the category is the category of twisted Yetter-Drinfeld modules in the category of modules for lambda OSP. So we had this ambient category of the tautological ring.
Yeah, but it's pretty abstract thing, because there are no, like relations, how you recognize anything inside of this category. Like if you're interested in, say, I don't know, twisted Yangian, there are generators, relations, anyway. There is some way to see them concretely, and this is Yetter-Drinfeld modules in a quite complicated category. Yeah, so it's how you connect it to with the real
Yeah, how
world.
do you reconstruct an algebra with relations? So The
Yeah.
hopefully you can kind of sort of see so that the relation in this twisted Yoder-Drinfeld condition is actually very similar to the relation in the standard Drinfeld double. So let's take actually maybe I'll do this on a new page at the bottom. So what is the usual like Yoder-Drinfeld condition for some ordinary Hopf algebra H? So H, let's take to be a finite dimensional Hopf algebra. So in this case, this Yoder-Drinfeld condition, the category of Yoder-Drinfeld modules for this algebra is equivalent to one, the center of the category of H mod, and it's also isomorphic to modules for DH, which is the Drinfeld double of that category. So from this kind of funny condition, we're able to just recover from the category of modules for a Hopf algebra, the category of modules for its double. So if H...
So what's the definition of the center of H mod?
Yeah, so maybe I'll give the example and then I'll tell you exactly what the center is. So if H is the category of let's say modules for UQ of n, where G
UQ of n is not a Hopf algebra.
Well, it's a Hopf algebra in not in vector spaces, but it's a Hopf algebra object in the category UQ of H mod. So it's a Hopf algebra object in an ambient braided category. And then the category of Yoder-Drinfeld modules in this ambient category is the category of modules which have actions and then also coactions. So we have an action map H tensor M to M. We have a coaction map from M to H tensor M. And then our condition looks extremely similar to the condition that we saw before. So if we write our module M, it's the same diagram under the assumption that our reflection is just the action of the antipode. So if this for reflection is just the antipode in the corresponding Hopf algebra, then this diagram being equal to this is this this Yoder-Drinfeld condition that allows us to recover the corresponding double. So algebraically, the relation between the action and the coaction, if we think that the coaction gives rise to an action by H dual, then this says that we have the following commutation relations. We get a commutation relation, a way of normal ordering the actions of H and of H star. And it says that if first we act by an element of an element H of H and then an element H star of capital H star, then H star followed by H is equal to this following like composition with the corresponding terms in the wrong order. So if we write the coproduct of an element using this notation of its H1 tensor H2, then this says that this tensor product is equal to the following thing. So we have H star 2, H2, then the pairing of H star 1 with H1, and then the pairing of H star 3 with the antipode of H3.
So Jeter-Drinfeld modules, they form monoidal categories themselves.
Yep, they do form a monoidal category, and they form actually a braided monoidal category. So
yeah, okay.
H mod form
and this
braided...
is abstract result. It's not about this particular.
Yeah, it's an abstract result, but it's a kind of beautiful way of recovering, in my opinion, the quantum group UQ of G from its positive half.
Yes, certainly. Yes. So recover in the categorical. So you consider Jeter-Drinfeld module for these Hopf algebra objects, and it's equivalent to the category of UQ of G modules. Yeah. Hold on. Something I do not. Hold on. I forgot everything, but when you say double Drinfeld double, you do not mean, you mean some modification of Drinfeld original definition, because he defined the double for the Hopf algebra in the category of vector spaces.
Yeah, so this is the double taking place in the category of modules for the diagonal part of that quantum group, and we have to do an additional step in order to recover the like relative double of UQ of B in vector spaces. So this is all taking place in this category of representations of the Cartan piece. And to recover like the usual Drinfeld double, we have to find a way to get to vect. So to get like UQ of G modules in vector spaces. So if we want to take, an actual V in vector space and an associative algebra in vector spaces with a map from UQ of G to endomorphisms of V, we use a process called Radford Majid Bosonization. So we take, which is a way of taking a Hopf algebra in well, it's a functor from H mod in an ambient category of modules for a different Hopf algebra T, and it sends it to modules for its cross product H tensor T mod. And in our case, this we go from UQ of n mod in the category of UQ of h mod. This gives us UQ of B mod, and the sort of relative Drinfeld doubling procedure is analogously we get a way of going from, let's see, now I don't want to say something incorrect about double bosonization. So yeah, usually the way this is phrased is we take modules for an appropriate double of UQ of B plus tensor UQ of B minus, and then we have this subspace UQ of G mod where the two diagonal pieces are forced to act in the same way. So you're right that there's a couple of steps to go from this categorical construction to an honest vector space with a corresponding action.
Sam, yeah, I mean, the different pieces of that were written somewhere in different times, because so either a place where it's kind of combined, I mean, in the condensed way.
Majid's book is pretty good.
He wrote a book. What?
Let's see. I'm forgetting the title of his book. Quantum groups is certainly in the title.
All right. So yeah. Okay.
But yeah. So Majid's book is a good place to learn this stuff. But
okay.
it.
Okay. Now I have a question. So
Okay.
Probably you read something in that book. If I replace UQ of n by the algebra of functions on the upper triassic, even for SLN, on the algebra of function on the upper triangular matrices. So how these things, what do you get?
Oh, what's the double you get in this case? So this algebra is naturally sort of the dual of UQ of n. So it's if we take the kind of we exchange the off product, the coproduct with the dual of the product and the product with the dual of the underlying multiplication map. Yeah, I've never actually thought about what the double gives in this case.
Yeah, you see, I am curious because that's kind of what I did many years ago. Actually also wrote a book. It's algebra of functions on the quantum. It's a dual object, but shifted Youngians, they are naturally, as far as I understand, quantizations of the quotients of the algebras of functions on the negative loops. Yeah, like
Functions and negative loops.
yeah,
Okay.
you take like you take this conventional Drinfeld double, like all loop splits in the positive and negative,
Sure.
like yeah, and you keep the negative part. With probably to get a group you require that it's Laurent series which start with identity at the level of group and just start with negative at the level of Libby algebras. But that's a construction of the shifted Yangians, I don't know, and it's a paper by 4 authors, Kautis, Kamnitzer, Webster, and Jacobi, probably. It's kind of a paper. When I look at it, I just recognize what I did in the finite dimensional case with the algebras of functions. And hopefully, if you apply to the dual thing, it's interesting because here you do not pay much attention to what modules do you consider. If I ask you, you say, okay, take finite dimensional and you'll be happy. But for the algebra of functions, for the dual thing, there are no finite dimensional representations, so one should be more careful. So formally it looks similar because you indeed start just with something dual. So anyway, so yeah, I wrote the whole book with a student about the algebras of functions, and they have many similarities in some sense with quantized enveloping algebras, but representation theory is totally different. So that's why I'm a bit kind of not sure whether this formal construction is that good. If when you try apply it, probably you know better, but you want to get a shifted Yangian, and shifted Yangian is naturally a quantization of the algebra of functions, as far as I remember those 4 guys.
I see. So we do seem to be able to recover like shifted Yangians. Again, there's a slight modification that I sort of mentioned about this sort of symmetry condition that we more or less understand how to get shifted Yangians. We haven't we have a construction that we expect recovers shifted Yangians. We haven't actually proven that the thing that we get is the shifted Yangian. So yeah, we do expect via not literally the process that I'm describing, but a slight modification of it, that we're able to recover the category of modules for shifted Yangians with its system of coproduct.
What finite dimensional modules? Or what?
We want to impose everything here needs to be graded over like the k num of our underlying abelian category, so that and then times the integers keeping track of cohomological dimension. And we want these to have finite dimensional graded pieces for this algebra.
What does it give in the case of shifted Yangians?
So we expect, so how do we recover shifted Yangians? So one way to get a shifted Yangian module is by taking the critical cohomology of, let's say, for this is going to be a shifted Yangian for if we have k arrows going this way, L arrows going this way, a one-dimensional vector space here, and our usual dimension vector here.
Either a cyclicity or stability condition on this moduli space.
Yeah, with the stability condition. Yeah, so semi-stable, the moduli representations of that quiver times K times L. So this is in this case that this is probably not the first time that this has been written down, but one place where I know you can find this is in Cow Okunkov Zhu, I'm forgetting who the last author of the paper is, but the critical stable envelopes paper.
But this is why you wanted symmetric quiver at the very beginning, because I asked Andrei whether they really want the quiver to be symmetric, and he replied me that it's better to be symmetric, which a bit strange. Yeah, it's kind of strange.
If you force symmetry, then you get for these tripled quivers with potential, then you get actual Yangian representations. And the asymmetry is precisely related to like what shift you get. So
This looks, I mean, I cannot immediately compute it in my head, but they look rather the Verma type modules. They do not look as finite dimensional unless you do some.
with the stability condition, these are
Yeah.
with the stability condition, I think this is finite dimensional, or at least roughly finite dimensional.
Hold on. No. It's just critical, but of this.
The cohomology of the semi-stable
No.
envelopes.
No. It doesn't look. Hold on. Mm, mm,
Is that is it finite dimensional? It should be some sort of bundle.
mm,
It's certainly not the size of a Verma module. It's yeah, I mean it's some module. And it may not be finite dimensional, I'm not really sure. But it certainly has finite dimensional pieces under this grading by
Yeah, but
dimensional.
I'm not saying that it's exactly Verma, but there is this category O, and every object is graded by Cartan. So then it's infinite sum of finite dimensional pieces.
Right.
Yeah, so but it doesn't prevent it. It looks rather this kind of, similar to this AGT stuff where you have cohomology of the moduli spaces of something stable, and you have, well, sort of a Kac-Moody type, quantized Kac-Moody type algebra, double CoHA, which acts on this cohomology. And this, so it gives you, it's something like analogous to the old Nakajima story when the Heisenberg is realized in the cohomology of some quiver variety, so it's not finite dimensional.
I see. So yeah, I mean I think that there are examples where exactly as you said for SL2 for some framing that you get something which isn't finite dimensional. So for example, the cohomology of the space of quasi-maps to some other quiver variety can be written as the critical cohomology of a quiver with potential in this way. And it should be a Verma module for the quantized Coulomb branch, which is exactly the some truncation of the shifted Yangian. So it's I don't think it's going to be a Verma for the shifted Yangian itself, but
yeah, for truncated. Yeah,
yeah.
you're right. For truncated, probably.
But so our rough expectation is that if you take an appropriate modification, so we modify the C lambda, then our chiral center of the category of and we'll call it C tilde lambda, C lambda tilde, the chiral center of A modules in the category C tilde, again imposing this condition that with respect to the finite dimensional carton, including the cohomological direction, it splits into finite dimensional weight pieces. The chiral A mod of C lambda in C lambda tilde, that this is like actually isomorphic to modules for the direct sum over all shifts W, which are all co-weights. Let's take the quiver finite dimensional, and these are co-weights of the maximal torus of W shifted Yangian of that corresponding finite dimensional group G. So yeah, this we expect to actually be true. And so but yeah, we don't have a proof of this statement, but
Now maybe you'll tell us what is a chiral center.
yeah. Yeah, so that was the plan. You know, so once we have you know, this setup, so what is our algebraic setup? Well, we have a braided commutative, co-commutative Hopf algebra object in this ambient braided category. And we have anti-involution on that category, gives an anti-involution on the algebra, and then we make some technical assumptions. The biggest one seems to be the existence of a vertex antipode, which geometrically we can show, for example, in the cases of quivers. Then, you know, we have a braided module category over that corresponding category, which is sort of modules for this coideal subalgebra of the underlying tautological ring. Then our chiral center of that category is going to consist of endomorphisms of the category of A mod. So they're functors from A mod to itself, together with, so they're pairs consisting of such a thing, together with a binatural isomorphism of the following two bifunctors. So we have a bifunctor, which is we apply F to the meromorphic tensor product of two elements in that category. And we want this to be isomorphic to the functor that we get by applying to just one side and then taking tensor product with n, together with appropriate compatibility isomorphisms with the swap, the translation, and associativity requirement. This is kind of what you get when you just stare at the usual notion of a center and replace the meromorphic tensor product with the underlying tensor product that you had before. And likewise, there's a folded version for modules where we require, you know, these two bifunctors to also have a natural transformation. And instead of being an endomorphism, we just have a functor from the category of A modules in this braided module category to A modules in that module category. You know, these are supposed to be kind of universal braidings of our supposed object with any other object with sort of similar compatibility requirements. And because of our description of these categories as you know, categories of either endofunctors or functors from one category to another, they're clearly monoidal. So we have a tensor product via composition of endofunctors, and then we have a module structure via composing some endofunctors with our resulting functor to this kind of exit category. And then the theorem says that not only is this monodal category, but we get a meromorphic braiding with explicit if with an explicit formula in terms of the data of the underlying algebra. And the work in progress is to show that the same thing is true in the folded case. And then the idea is that we can translate this language under technical assumptions into the type of modules that we can construct geometrically. At the very least, we get a forgetful functor from this folded category to the category of twisted Orientifold modules, and we can construct geometrically objects in this central category from geometric bimodule objects that we get using moduli stacks in the corresponding category. And then observation, which is the first thing that we should notice, is that given fiber functors from these underlying categories, then endomorphisms of this sort of fiber functor for the folded category is a co-ideal subalgebra of endomorphisms of fiber functor of the original category. And so the hope is that we can use this construction in order to reconstruct the category of modules for twisted Yangians from the positive half of the Yangian itself. Likewise, we have from exactly the construction that we gave, we can recover the commutation relations in the Yangian itself, at least of SL2, but probably for all finite type A. And as I mentioned, we expect to be able to recover shifted Yangians by precisely the same process. And that was all I wanted to explain.
Yeah, thank you very much. So, all right. So, I don't know. First, if you applied not to the quiver with potential framework, but pure geometric, yeah. So you have CoHA and like to this example, which coherent shifts on three-dimensional Calabi-Yau. What will you recover?
Yeah, so what this gives us is some braided category under this assumption of a vertex antipode, which says something about finite nice Jordan-Holder filtrations, which should work for any compact Calabi-Yau threefold. Unfortunately, in this case, it's it's not like we have a general theorem that says for an arbitrary Calabi-Yau threefold, we can construct like a bunch of objects in this category. So this is one thing that's missing that we would like to have is a way of sort of saying a broad class of geometric examples that we get modules. We have expectations of what we would get. So for example, if you take torsion sheaves on the Calabi-Yau threefold, that you should get module. And so that's our abelian category, that we should produce natural objects in the center from torsion-free sheaves on the same Calabi-Yau threefold. And then if we could show that those are elements of the center, then it would naturally give us R matrices for those representations.
Yeah, you see, for me, kind of a torsion-free sheaves, well, torsion shifts, it's sort of Cartan somewhere, and torsion free, it's like n plus. So giving them together, you can reconstruct uh, some modules of sort of a double CoHA, whatever this means. Yeah, and another question, you mentioned mutations, so, and also, I like Orientifold, but I'm more interested in the category of lines themselves. So, what happens to cluster structure? Should it be very specific that I should apply it to whatever BFN moduli space, blah, 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 or because there is a quite abstract definition of cluster category, this Hernandez, another thing, people.
Yeah,
So,
so you know, the like, and again, I think we certainly expect this category of the chiral center passes a lot of kind of consistency checks that you might want. So we certainly expect that the that this category when we at least sort of let's take sort of simple cases of a quiver with a node, that if the node is a source or a sink, that we get a nice categorical equivalences between the centers by applying mutations to the corresponding functors. But again, it's relatively new stuff, so we haven't we haven't managed to show this yet.
and by the way, again, like returning to the time when I was of your age, this algebra of functions on quantum groups, you see, you do not have quasi-triangular structure, they're different. And so you do not have Young-Baxter equation, which originally was a condition of integrability, yeah, in 2D lattice models. But instead, you have the Molodchikov tetrahedra equation, which I don't know what kind of interpretation it can be obtained from this type of formalism, because your this formalism is designed to get R matrices, because it's more or less you reproduce something like double of and the reason for the Molodchikov tetrahedra, I have no idea actually. I thought about it long ago, but there was a relatively recent, maybe a couple of years ago, work of a guy from Yale Institute, I think Yagi. He actually he has, I believe, joint paper he had with Kevin, and he is in China now, about integrable lattice models and the Molodchikov tetrahedra. And of course, he is a physicist, so which means that it's difficult to understand what he's talking about. But formulas in his paper, it's exactly formulas which I wrote long ago for representation theory of quantized algebra of functions and their tensor products. And also there is, maybe you heard this term, quantum Weil group. So when you have the R matrix, you have a representation of the braid group. So that's the name of the braid. Okay, braided monoidal category. And using this dual object, algebra of function, quantized coordinate rings, you can quantize the Weil group of your G. It can not necessarily finite dimensional, though I did it finally. So, and you get something which is between the braid group and the while group. So it's some kind of interesting object, and probably all this is responsible for certain integrability in 5 dimensions. So then the question is, if I try to apply, at some point probably it will not work, but I really don't know if instead of your A, which is in the example is UQ of n, 1/2 of the quantum, you start with algebra of functions on the quantized unipotent group.
I see.
So I have no idea. Certainly you will not get, you should not get algebra of functions on the whole group, because from your construction you get something quasi-triangular, and that it's not. But you get something. So I'm just curious whether kind of Majid is fine, okay, but it's kind of old stuff. Maybe
Sure.
you can within this factorization business get some higher integrability conditions.
I see. So you were saying that from you can see the tetrahedron equation from just functions on the group and
From functions on the okay, formally you quantized algebra of functions on the group. I don't know, like SL2, for example. This is fine. It's easy to describe in terms of R matrices. All right. And then you consider it at roots of unity. All right. And then it does have some nice representations. I mean, which I forgot, finite or not finite dimensional, maybe even finite dimensional. And then you can, tensoring these representations, you can see the homologic of tetrahedra. Long ago, I believe it's, I don't remember, the beginning of 90s, we wrote a paper with Kazhdan about the homologic of tetrahedra, but before us, there was a more fundamental paper by Kapranov and Voevodsky, how the homologic of tetrahedra equations come from the formalism of two vector spaces, two categories. Yeah. So again, it was kind of a well forgotten, but recently I exchanged some emails with Yagi, but he did not probably recognize the potential. He is a physicist. He is interested in some integrable models. You can find his papers in the archive.
yeah, we're actually kind of reading with at PI. We're sort of trying to read through his papers and also the same ones that you mentioned to try to
Yeah,
precisely understand how to
but the
write them.
thing is that the formulas which he wrote, I can find, I can pull up my exchange of emails with him. But formulas he wrote, it exactly formulas for the representations of the algebra of functions on the quantized SL2.
And then do you see a chiral tensor product structure here if you take, for
No,
example, that
I
function?
don't. Well, no. I wanted to get something for, yeah, I asked them a question which is not equivalent but closely related to that. But he did not reply. But he put some, like he's a physicist, some M-branes, parallel
Yeah.
M-branes, whatever.
Wow.
Well, but the formulas which he gets in the end, for me, it looks like he tensored several representations of a quantum algebra of functions on SL2. And the point is that the homologic of tetrahedra comes from the intertwiner operator. You see, if your R matrix, it's like A tensor B is isomorphic to B tensor A plus compatibility. Now, if you take associativity, A tensor B tensor C, so you get some, for UQ of G, it's some trivial, it's strict associativity. For algebra of functions, it's more tricky. And this tricky associativity, it satisfies the homologic of tetrahedra equation. I can find this paper with Kazhdanis was published in some strange proceedings volume. I'm not sure you can get, but maybe I have a copy. If you like, I can send it to you. Yeah, but the point is that you have this formalism, which actually I like it because it's kind of you reproduce the category. Yeah, I know Majid, we wrote long ago a paper with him, maybe a couple of papers, but I didn't read his book. Yeah, and so what will happen if we apply this to the dual object? That's funny. Yeah, good. All right, so more questions.
Yes.
Okay.
Actually, I'm reading your paper. Just a quick question. And for the short exact sequence SES, that's fine. But in your paper, you're using the SES sub 3. So I wasn't quite sure what's.
This is the convolution of two copies of SES. So it's
Can
we
you?
take SES composed with SES.
Yeah.
And so this
how
is this
you compose in what sense? You have a two short
the
exact
convolution over
sequences.
the central term. So it's like on m times m. So this is something that goes to m times m, starting from the, we have on m times m, we have SES times m, and then that goes times m, and then we have m times SES, which also goes here. And it's the pullback of these two diagrams.
I just don't. It's not anything that is about 3 terms or 4 terms of short exact sequence, or
that it's closely related to 3-term short exact sequence, right? So that
it should be with the 4 terms, you mean, or 3 terms.
Well, there's 3 terms. So it's the diagram that we take fixed points of. So it looks like it's like a composition of 2 short exact sequences.
So
if we
that's
have,
what I don't understand when we compose 2 short exact sequences.
So we have A and C. So this is this diagram here that we have. So if we have here's A, B, C, and D, its composition can also be encoded in this diagram. So first we take a short exact sequence. So all of the rows and columns of this diagram are exact. And here we have whatever the extension is that we get E. And here we have D.
Yeah.
So then we're going to take the central term of the thing we get the extension of E, and then we're going to take its short exact sequence by C to get this term D. And so D is that remaining term, and then we also have, some F. So you can encode the diagram of the composition of these two things into it automatically gives you this extra data of B, because it can
the composition is the top exact sequence and also the right vertical exact sequence.
Yeah, which recovers, you can see it in either way. So somehow you can start
the middle one, which gives the or I can just regard the SES3 as the entire diagram.
Of this entire diagram, but you can recover the data of the diagram from just some of the pieces. By I'm forgetting which lemma and
okay, yeah, I see.
So once you know A, B, C, E, and D, you know B, but you can also recover F, but you can also recover you can recover F from E or E from F.
Yeah. Okay, I see. Okay, thank you. Oh, actually, one more question. So you were using but involution because here you were using cohomological, and which is very nice. But in cases of the one takes the constructible perverse shifts, this is what Lustig did for the quivers, not only for the order 2 automorphisms of the, but he was doing the order 2 automorphisms, not the eta automorphism, and
Right.
constructed all other non-simple list quantum groups. So
Yeah. So this is something about kind of twisted, like I think there's something like uniquely affine about this anti-involution story. Yeah, I'm not so sure, but it's you can also include a higher order. So for example, this Simatuzi, there's no way for it to really like be any other group because it's something about like reversing arrows or taking like duals. Yeah, it's something about reversing
yeah, so
arrows.
for example, to get the G2, one start with a D4, and this time you will need the order 3. Actually, it's the symmetric group of order 3 acting on this on
Yeah,
the Dinkin diagram of D4 and the orbits. Kind
yeah,
of a Dinkin diagram folding that gives the G2.
right. Yeah. So I've spent way too much time trying to figure out how to get that example to work in this formalism, and have not been successful.
Yeah, that's what Lustig didn't do. The eta automorphism, just the reversing the using the involution or reversing the arrow. Lustig was just simply using the preserving the arrow direction and
Yeah.
using automorphisms, so that one can go for any order. And you instead of taking, he was taking equivalent under that group or finite group action.
Yeah.
Equivalent constructible perverse shifts, and constructed all this quantum half of the quantum enveloping algebra for almost any quiver. But in time of constructing the canonical basis or crystal basis, whatever that's called, he was having some difficulties. There was still a sign issue, but I'm wondering if you could follow what Lustig did, using the automorphisms instead of eta automorphism to do the cohomological whole algebra construction.
Yeah, it's good, actually the good point, because what's going on, Lustig used rather in this motivic shifts on the stack, and you use coherent shifts, so it's a different story. So it's indeed like it's an old question that, for example, at the level of DT invariants, you can use CoHA, you can use motivic whole algebras, and you get in the end the same DT invariants. But why? I mean, they are completely different. It's constructible shifts and coherent shifts. And similarly, there is, constructible Satake, which is classical. There is coherent Satake. And so it's two different, constructible perverse shifts, coherent perverse shifts. At first glance, for these purposes, coherent shifts is right language, right category. All right,
Well,
so
for me, there were too many coherent shifts, and the constructible shifts is very sparse, so that's easier to compute. But turned out that the coherent perverse shifts are not too bad.
yeah, there are maybe more fundamental reasons for that. All right. So Sam, I ask you to send me updated notes. You make some corrections during your talk, so please. Also, I found this, and unfortunately, it's a whole volume with our paper with Kazhdan. It's like 18 megs. I send it to you, but whether the internet will deliver, I do not guarantee.
Okay, yeah,
Yeah, but anyway, it's on the way
great.
to perimeter. All right. Well, thank you very much. Very interesting course and new ideas, and we are looking forward for your paper
Yeah,
with Alyosha.
yeah, thanks
Thanks.
so much for the invitation.
Thank you. This is it for today. Thank you.